So hi everyone. So welcome to today's talk. It's gonna be about molecular generation. What are the kind of new things that are happening in that space? And so I try to give a more intuitive picture of this, but there would be lots of probably technical material, so we'll quickly go through it because we probably won't have time to go in details. And this is joint work with several people who are present in the audience. Yogesh, Mauri, Diego, then Gian is a student at University of Manchester. Andre Freitas is also a faculty at University of Manchester, and then of course Marcus and some. So, I think we need to probably move this. Just a second, this bar should not go there. This is better. So, why are we interested in this problem? Because generating molecules and macromolecules, it holds key to designing new drugs, materials, batteries, fuels, catalysts. So it opens up lots of opportunities, and that's why we are interested in this broad setting of drug design and material discovery. In order to make this possible, however, certain challenges need to be overcome. First of all, the search space is really huge. It's a combinatorial space. So, for example, even when you consider small, drug-like molecules, there are estimates that possibly 10 raised to power 60 drug-like structures exist, though only a very tiny fraction of these, of the order of 10 raised to power 8, have been synthesized so far. So this is really a huge space. And if you even push this further, for example, if you talk about proteins, there are 20 amino acids, and if you have a length and chain polypeptide chain, then you have 20 raised to power n possibilities. So it's and so it's not unusual to have thousands or several thousand long chains. So you can well imagine what space we are really talking about. And then, besides that, it's hard to generate valid candidates intrinsically. So what do I mean by that? So generally, for most of the methods, or pretty much all the methods that at least we know of, the way they work is they need to resort to some kind of valency checks or some post hoc correction in able to generate valid molecules. So valency checks, for example, carbon has valency 4. So it can attach to like four other atoms in its vicinity, and so you would generate molecules that would not be valid, and this is a major problem that many of the existing methods suffer from. So one of the things that we would try to look into is that, as you can see from this table, the validity percentage, they seriously take a hit, and these are really very low numbers, and the idea is, could we really push this further? Without, in some ways, we will try to model the underlying physics, and then try to understand if, without doing any of these checks or correction, could we still learn to generate a high fraction of molecules that are valid? There is also another problem which becomes quite interesting. So generally, there are different factors, and here by factors I mean the latent representations, or you could think of these as essentially latent subspaces, which are responsible for different properties. And what you would like to do is to be able to separate these properties in some ways. And the motivation could be, for example, if it were a supervised setting, then you might want to suppress toxicity. Suppose there are different properties like bioactivity, toxicity, and so on. So there are certain properties that you would like to suppress, and others you would like to enhance in some way. So you would like to generate molecules that are not toxic and satisfy other properties. And this is a very practical concern, because about 1/3 of all drug candidates that are there, they fail clinical trials due to, for example, toxicity. So this is a major problem. So could we take, for example, some step towards getting these disentangled representations, especially in an unsupervised setting where we don't even probably have the properties? It's not always possible to do so. Like it's not that, I mean, if it were ideal, then probably people could do some things. So some of the properties may not be, disengageable from each other. And so we will see how do we account for this, some partial notion of disentanglement. By the way, please feel free to ask any questions at any point of time. So for the purpose of this talk, we'll focus on small molecules. I was talking about proteins and, like these larger macromolecules, which could be, really huge. So the kind of methods and techniques that we apply generally vary. And so for the purpose of this talk, we will focus on the small molecules, which is like, you could think of about 30, 40, or maybe let's say 60 atoms each. If you are interested more in the protein design, larger macromolecules, this is one of the papers that you could probably check out. So to be specific, here is the agenda for today. First of all, I'll talk about modular flows. This is like, as I said, this is our attempt to generate molecules with high intrinsic validity. So we will not be relying on any external checks or post-hoc correction measures. Then I would show how these flows can be viewed as, like in some ways, a continuous version of temporal graph networks, a specific variant of temporal graph networks. And then the question arises, how powerful temporal graph networks could you get for modeling dynamic interactions, for embedding dynamic graphs? And so I'll be talking about some results which essentially, lead us to the most powerful temporal graph network that we know as of today. Finally, as I said, I would move on to this new notion of conditional disentanglement. This is a symmetry-induced notion. So I would not specifically be talking about the group theory at all, because in half an hour you can do only as much, not more. But certainly, I hope that at least some of the intuition I would be able to convey nonetheless. So I suppose most of you would be familiar with generative models, but in case you are not, here is a very quick, one slide for generative models. So typically, in context of generative models, the idea is that we would like to learn latent representations, like a mapping from the original space to latent representations, and then a mapping back in such a way that you are able to generate new data. For example, I give you a bunch of molecules, and then I would like to generate more molecules that are similar to these molecules. So this is not a classification task. I'm not asking you about say, for example, predicting the property of a molecule. This is more of a generation task. And so, for example, here your X would be, say, a molecule. Then you would have, let's consider VAE and flow-based models. So let's focus on second and third for the purpose of this talk. So your X could be, for example, your molecule. Then your encoder could be, for example, a graph neural network encoder or some other structured encoder that will give you an embedding for the input molecule. And then you also have a decoder, which essentially tries to reconstruct from the latent representation to the, it tries to reconstruct the original molecule. Now there is a catch, because you are interested in generating new data or new molecules. So what you try to do is to encode some kind of trial on the distribution of on the latent space. And so when it comes to generating new data, you could just sample from that according to that distribution. And this is generally a very tractable distribution, like a Gaussian or something of that form. And then you can just feed it through the decoder in order to recover, a new molecule, for example, in order to produce a new molecule. And that's how this works. During training, you are trying to get latent representations, but impose some kind of, distributional assumptions. For example, via a KL divergence or any other kind of discrepancy measure. And then at the time of generation, you just sample from the latent space because there is no input molecule then, and then you try to decode a new molecule. So flow-based models essentially take this VAE step just like a bit further. So now you essentially apply a series of invertible transformations. So in case of VAE, typically your latent representation is much smaller than your original or the ambient dimension. But in case of flow-based models, typically you resort to invertible transformations. And the idea is that even if you have a bunch of molecules or data that has an underlying complex distribution, you could still start from a somewhat tractable distribution like a Gaussian, for instance, and then by using a series of invertible transformations, you can get an arbitrarily complex continuous distribution. And so this is how you essentially do. So now encoder and decoder are essentially invertible. And rather than having just one step, you have multiple steps or compositions of invertible transformations. So these two are of main interest to us. So how do we go from flows to what we call modular flows? So there are some steps, and these are kind of mechanistic steps. First of all, molecules can be represented as 3D graphs or trees. These are the representations that we could use for our purpose. So here is an illustration. You are given some input molecule, and you can just represent it in terms of this graph. And then you can further, if you have, for example, some ring-like structures, you could replace those with a new node. So this essentially amounts to increasing your vocabulary. So for example, originally you might have carbon, nitrogen, oxygen, sulfur, hydrogen. These are the atoms that you're trying to predict. But now you could also have these ring-like structures that treat as a single entity. And so now you can also learn to predict rings instead of individual atoms. Now, generally, as I mentioned, when we speak of normalizing flows or the flow-based models, you start from a tractable distribution. So you sample from that, apply a series of invertible transformations, and then you get a complex density at the end. For our setting, what we essentially do is you take this structure without the node labels. So you for example created a graph or a tree representation, but you kind of hide the node labels. And then what you do is you first begin with an individual flow. So this could be just like independent Gaussians at each node. And then over a period of time, what you try to do is after it's a multi-step procedure, and after each step, the nodes interact with their neighbors. These are local update steps, and they try to update their density. So what the idea would be, you should think of it like saying that the nodes start from their marginal densities, and by interacting with their neighbors repeatedly, so that you are aware of the local neighborhood, they all move towards a joint density, and so that's the idea from which you can then sample the labels and does the molecule. And so this is also illustrated here. For example, it's easy to see here. The overall picture looks like this. So what we are trying to do is to still retain this notion of invertibility of flow in some ways. So previously also flow-based models have been used, but generally what happens is there is some kind of segregation or separation between the edges and the nodes. So you would, for example, generate some nodes, and then you will try to generate some edges, and that leads to some kind of distributional shift from your original data. Here we are trying to mitigate that problem. So here, first of all, you have many steps of this flow, this coupled flow, which is essentially a PD system. And then once you have done sufficient amount of interaction between the neighbors, then you essentially apply a softmax and an argmax. This process is clearly, because of the argmax, this process is clearly not invertible. And so there is an invertible part, which is this, the flow, and then there is a non-invertible part, which you see here. And in terms of the objective, what we essentially are trying to do is to minimize the KL divergence between the data distribution and the parameterized model, your flow model. And as I said, this essentially amounts to coupled OD system. And so here are, for example, the representations of the individual nodes. So each node gets some feedback from its neighboring node. So this is essentially a message passing, local message passing step. And likewise, it also sends across its current embedding to its neighbors. So this is a function of time. We set up essentially a differential equation, one per node, but these differential equations are coupled. And so you can take into account also the geometric information. For example, if you have 3D coordinates associated with the nodes, but it's all essentially a local message passing step at each node. And here is an illustration of how just a toy example. And so you can stack all of these together. You get your PD system, and then you can solve the dynamics, and there are differentiable OD solvers that are already out there. So here we talk about some of the results. As you can see, we are not doing any correction here, and there are no checks, and still we are almost getting like clearly above 95%, 96%. Results. So validity, with respect to validity, so the molecules that you generate are likely valid. And there are other metrics also that are of interest. For example, uniqueness. You don't want to be generating exactly the same molecules over and over again. And so uniqueness is the fraction of the molecules that you generate that are not duplicates of others. There is also this, like novelty. Novelty essentially is a criteria to measure how many new molecules that you are able to generate. Essentially, the molecules that you did not see as part of your training, but you're able to generate after you trained your module. And then, of course, reconstruction. So reconstruction is a slightly easier task, essentially, for these flow-based models, because you have some notion of invertibility, and so typically you can do that. And here you also see for 2D, here is for two-dimensional. 3D is when you take the 3D coordinates, geometric coordinates into account. TGNN here is for equivariant graph neural network. So you can really the function f theta that you see here, you can make it equivariant. So essentially, you can take into account the rotations and rotations and translations, and your representation essentially reflects that. Yeah, so these are the standard metrics, and in some sense like some kind of sanity checks, but there are other metrics which are more stricter in some ways, and which try to capture, for example, how likely you are to be a drug. So there are different kinds of things there, and it performs really well across these metrics. Some more results. So there is also like this check that we perform, which is whether it's able to learn the underlying densities well or not. And so here you see, for example, these stripes and these chessboard and other kinds of patterns. And so these are binary patterns affecting 0, 1 for different colors. And so this is essentially like a highly discontinuous functions, there are densities that we are trying to model, but Modular is able to successfully learn this. So this is a sanity check. We know this, we understand this problem well. So so this is good. Then there is also another thing which is of interest, which is property targeted molecular optimization. So here the idea is that you start with, for example, some molecule or latent representation, and then you're trying to take gradient steps towards towards molecules that have a higher value on a desired property. And so this also seems to work well. So you can see that we started with, QED is quantitative estimation of drug likeness. It essentially captures how likely your molecule is, to be a drug. And so by taking these gradient steps in the latent space and then decoding it back, we are able to get molecules that have a higher score, a higher QED score. There are other kinds of things that are important, which are these low P QED, synthetic accessibility, and then molecular weight. And so here the idea is we want to see the statistics of the generated data. The new molecules that you are generated, are they really close to the training data in some sense or not? And these are the properties that you care about. So, so QM9, it does really, really very well. If you see, like, essentially on all the four properties. With respect to Gene 250K, there is clearly some deviation here. So this can be improved. Okay, any questions at this point? No? Very good. So we come to the second part of our talk today. So one interesting thing that comes out of this is that modular flows can be viewed as a kind of temporal graph network. And so what do I mean by that? In case of temporal graph networks, you are interested in, for example, so you have dynamic graphs and you have these different nodes, and you're trying to predict, for example, whether for a given pair of nodes, they would interact in future at a specific point of time, for example. Or you may want to classify the nodes at certain times. So this workflow can be in some ways viewed as a equivariant temporal graph network. So here, for example, you have a node I and its neighbor J. And if an event or interaction happens between I and J at time t, then, first of all, this is a message step. So this takes into account the last update of node I, which was a state. So each node maintains a state or a memory with itself, so which kind of gets updated every time it interacts with some other node. And EIJ is the nature of the interactions. It's essentially like a bond features or that. And so then a node essentially aggregates the information from all the events that it's involved in over a small amount of time. It updates its memory state, and then that is used to finally update its latent representation. So very similarly, there is an analogy with mode flow as well, and you sort of get that it's an equivariant temporal graph network using the mapping that you see there. So now this brings us to the next question, that if there is this kind of correspondence or some rough relationship between temporal graph networks and modular flows, could we design more powerful temporal graph networks? Because then in principle you could also get better models of flows for representing the molecules. And so this is where it gets interesting. So usually the temporal graph networks, they can be broadly classified into two types. First are so-called the message passing temporal graph networks. These are very reminiscent of the static graph neural networks, message passing graph neural networks that you might have encountered. And so like it's essentially, for example, the graph is missing. That's interesting. Yeah, so you should see this, that you have a V, and then V's neighbor is U, and then so V has two edges here. Let's just draw the graph. So you will have a node V, then there is a node U. V interacts with U at time T1 and T4, and then V interacts with Z at time T2. And then there might be other nodes W, for example, that might be interacting with this. So usually when you, for example, talk about graph neural networks or temporal graph networks that resort to message passing, for example. So what you do is you kind of trace the evolution of the information. How does the information propagate? So, for example, if you want to see with respect to V, you get a computation tree. Essentially, this is called a computation tree. So, V is connected to U at time T1, then it's again interacting with U at time T4, and then it's interacting with Z at time T3. Now you can further unroll it for the next time step with U, and so U is connected to V at time T1, and then again T4, and so you can just associate a computation tree for each node that's out there. And now you can essentially think of aggregating the information bottom. So whatever is the number of times that you unroll it, and the flow of information is bottom. And so that gives you the kind of final embedding for each node. On the other hand, so these are the message passing temporal graph networks. On the other hand, you also have the walk aggregating temporal graph networks. And here the idea is, instead of taking this, like breadth first information, you will try to take walks, random walks from the node. So for example, in this case, with respect to V, you take, this is one path, for example, V to V. And then you have another V to V, and then so on. And so what you will try to do is take these paths, treat them as sequences essentially, and feed through, say, a recurrent neural network. And that gives you, embedding for the entire sequence. And so this is what is called the walk aggregating temporal graph network. And it turns out that, neither of these is subsumed within the other in terms of expressivity. Neither model is more powerful than the other. So there are some cases for which the message passing temporal graph networks are better. For other cases where the walk aggregating temporal graph network should be preferred. And there are other kinds of interesting things that also unravel. For example, if your message passing temporal graph networks are sufficiently deep, and by sufficient I mean here, for example, order of the diameter of the graph that you get at any time instant. If you are deeper than that, then essentially you do not need memory at all. So if what it essentially suggests is that you just need as many or nearly as many layers as the diameter of the graph, and then you can remove this. As I said, there is a state update that's being done. So every time each node updates its state before before updating its latent information. And so these kinds of results show up. And the message passing temporal graph networks also have a correspondence with a temporal version of the Weisfiller-Lehman test, or the so-called color refinement algorithms. I would not go into the details of this, but suffices to say that there is lots of interesting stuff in this space. Oh, yeah, okay. This works. So I think I drew the right graph, more or less. And so, as I said, that you essentially take the paths, you feed them to RNN, and then you do some embedding that you use. Okay, so now a natural idea would be: is there a systematic way, for example, to combine? Because none of these class of models, temporal graph networks, subsumes the other. So is there a way to benefit from the strengths of both of these? And it turns out that yes, you can do that. And this is exactly what we do as part of this new model, which we call PINT. So this is position encoded inductive temporal graph network. And it is probably more powerful than the two versions that I talked about, the most popular class of the temporal graph networks. And the idea is again, like, I mean, you try to aggregate these features, and at the same time, you do some injective message passing updates as well. And this seems to work quite well in practice. For example, here the blue colored numbers correspond to the best performing model on a data set. So you can see the two tasks, the transductive and the inductive tasks. In case of transductive, we are only predicting the task is link prediction, whether an event will happen between a chosen pair of nodes. In case of transductive, we actually only restrict ourselves to the nodes that the model has already seen. So there are no new models, but you're trying to predict interactions between these nodes. In case of inductive, you allow for even new nodes. And so it's a harder task. But on some of the data sets, it clearly provides a considerable benefit. For example, you can see here, so it seems to work well. And there is also this ablation study that was done. For example, if you remove the positional features, and the positional features come from the walk aggregation. So if you remove that, then the like the model is closer to the message passing TGN, and the performance also goes down. Okay, so we come to the final part, which will be quite quick. Any questions at this point of time? All right. Are the people still with us on the other side? Yeah. Okay. So now coming to the final piece of the puzzle, disentanglement is a notion which has been really well studied over the last few years. The idea is, for example, you want to separate out. Suppose you take an image, and you have these objects. These objects could have different colors, different shapes, different sizes. And what you want to do is to learn a representation that is specific to size, that influences only shape, and that influences only color. So you want to learn the subspaces of your latent space that are completely separate from each other. In other words, it means that if you are able to learn a disentangled representation, for example, then what could happen is if you change the subspace pertaining to only the color, then it will not have any influence on the shape or size. So you can take an object, only focus on the part that gives it color or shape or size, one of these, and change it without affecting the others. And so that's the notion. So let's play this. Yeah. So you see, for example, here the shape changes, but the rest of the things remain the same, and likewise color changes in the background, but this. So it's not really intuitive. In case of images, for example, with objects, it's quite intuitive what you mean by disentanglement. The notion gets like a bit more subtle when it comes to graphs. How do you define the disentanglement on graphs? But for example, one illustration which has been previously studied is this, that there is a node U, which has lots of these neighbors, and only some of these neighbors, for example, are related to their work. So for example, this is a person, and these are like the people in their team or whoever they interact at their workplace, and other factor could be their families and their hobbies. And so one could think in some ways that you should be able to represent, if there is this clear separation of these factors or interactions, then you should be able to learn these disentangled representations. But this gets a bit tricky because it's not always clear that you could do, like you could You could also have some of the nodes that could overlap in principle. It's not the separation is not always there. And this is particularly true when we speak of, for example, molecules. You cannot just separate saying that this part gives it all the toxicity and this part gives it all the bioactivity. Typically, you would have overlaps or intersections amongst the nodes or substructures. And so in order to try to understand this situation, we introduce what we call this conditional symmetry for disentanglement. Here, the idea is that instead of demanding that all your subspaces, each subspace, pertains to a latent factor, instead of demanding that all your subspaces are completely separable from each other, which means changing one does not have any impact on the others. We say that there are disentangled parts and there are also coupled parts. So there are some parts of the latent space which in fact depend on more than a property, and you cannot just separate them. And so I would not go. We probably don't have time to go into the details. And the idea then would be you have an input graph, and so representing its adjacency matrix and probably the node and the edge features. Then you have a graph encoder. This could be, for example, a graph neural network or a graph convolutional network. And then what you try to do is in this latent space, you're trying to find these generative factors using some kind of Lie algebra based notions. And once you segregate these factors, then you can essentially put them back. But as I said, now there is also a conditional dependence in the sense that if you were to only combine these disentangled factors, you might lose out on some information. Because as I said, the assumption is that there might be some parts which are not disentangable. So what you do is you also provide this latent embedding again. So there is a detachable or disentangable part of information that comes from this E group, and then you also have this connection which makes up for the rest of the information that you possibly missed out on. And so this is essentially you can define essentially a lower bound very similar to elbow for this kind of problem, and you can maximize it. Just to show like how this works, for example, here is a data set which is this WS random graph, and here you have certain factors. These factors are the number of nodes that you have in the graph, then the probability P of which is the connectivity, which is the probability with which you choose a pair of nodes, and with certain probability P you have an edge between them, and so very similar to the Ardishleni random graphs. But then you also have other factor which is the k nearest neighborhood, and so this depends on the nodes and the connectivity pattern. So you don't have the full independence between the factors, so as to speak of. And so what we do is we associate a different color with each node, and then when you learn through this conditional disentanglement notion, so you could see, for example, if you go along the z naught axis, it kind of controls the color. Here you have the blue color, and as you go increase in this direction, the color kind of fades. So Z naught essentially is the subspace which controls your colors. Then Z1 is about connectivity. So you would see more connections between the nodes or less connections as you go in one direction. Then Z2 essentially controls the number of nodes that you have. So the number of nodes increases as you go up, for example, along one of the dimensions. So it seems to capture this notion that even when you have not fully disengageable latent subspaces, you can still learn from them and work with them. And this is surprising. So I talked about the VAE version, that the picture that I showed, but in principle you could also use the same idea in a flow-based model. And interestingly, it even improves upon the pretty much some of the state-of-the-art methods just by plugging in that disentanglement component. You can clearly see the log P and the QP properties that we discussed about in mode flow. You really improve on these. And also with respect to you could perform classification. So you first get these latent representations, and then you use those for training and prediction on certain data sets. And so even with a compressed model, the accuracy is improved upon. So you get succinct representations which are able to do well on the downstream classification task. So this is interesting. So this suggests that disentanglement, even beyond the factors of interpretability or like trying to enhance one property possibly at the expense of the other, even beyond that, you can improve the metrics that we really care about, just by incorporating a disentangled conditional notion of disentanglement. So yeah, so to conclude, such design problems are challenging, but clearly AI has a great role to play, across domains. It opens up several opportunities. The area is inherently interdisciplinary, like from ODs to temporal graph networks to group theory to everything seems to come together in this space. And in fact, like any advances that you may typically require you to make some innovations in terms of either the representation or the dynamics or similarly other things. And one of the important things that emerges from this is typically you need to understand the limitations of the existing methods. I mean, this is true in general for machine learning, but I think here in particular, you have to really understand where the existing methods fall short. For example, can the representations be more expressive? Or, for example, can you separate out as we saw here, could we separate out the factors that are really responsible without trying to separate out those that are clearly not disengageable? So yeah, so it's a very interesting space of problems. Hopefully, I was able to communicate some flavor of it to you, and I'm happy to take any questions if you have. Any questions?
Yes, one question about the first paper. So I just curious about input data. So you have a molecule.
Yes.
And how do you encode that, or what kind of molecule? So you mentioned like it's a protein.
This is not protein. These are small molecules.
Small molecules. So what the nodes are the
atoms? Nodes are atoms.
Yeah. So they are like there are 10 different items.
Yeah. Like.
Okay. And then do you consider how do you consider the order of the items? Like
you don't, because each node only interacts with its neighbors, and that's a set.
Okay.
So you don't really, so they are independent. So we associate these different flows, one per node. They start out independently and then they interact with their neighbors to update themselves. So
okay, so basically your input are different, all different nodes in the
yes. So you will have like essentially, if you have n nodes in the tree of the graph representation, depending on which representation you choose.
Yeah.
You would have n flows. So n differential equations you would be tracking.
I see. Okay. And another question is about the validity. So in the table you said you showed an example about the validity, and then I'm just curious, like because these are artificial generated molecules. So actually, how do you calculate the validity?
You just check, for example, for each atom. So you predict, for example, carbon.
Yeah.
And then you see like whether the atoms that it is connected, the bonds that it is involved in is 4 or not. This is just a simple local valency check.
Okay.
So for example, for oxygen, you know that it can have only 2 bonds. Nitrogen can have 3. So you want to ensure that like in your molecule, each of the nodes that's there that satisfies this criteria.
Okay, so basically, what is the validity check means like you generate some kind of molecule and then you want to really count like whether this kind
this
of
is well formed or not. Yes, this is valid or not.
Okay.
Because this is essentially like when we speak of bonds, it's about density. Like like so if a double bond is there between say carbon oxygen, that kind of gives you the density underlying, the distance at which like the atoms are or the electrons are supposed to be supposed to be there. So this is
but your input is like n flows and your output is also n flows.
Input is a graph. This input is a molecular graph.
Okay.
And then what we do is we take away the labels of the nodes. We associate just like a Gaussian density with each node. And then these densities, you have other information, for example, the geometric information of their neighbors, and then you aggregate this information from your neighbors, then you update your local distribution, and each node keeps on doing that for a certain number of iterations. And then at the end of it, you do an argmax. This was that procedure that I was.
Like n nodes.
Sorry, say that again.
So basically your input is n nodes and your output is also
n nodes. Yes.
N nodes. Okay.
Yes.
Okay. But then the edge between any two nodes.
We don't specify, for example, if it's a double bond or a single bond. First of all, it's just like the connectivity. You don't know whether it's like when you are predicting, and there still, even if you fix that topology. So if you have, for example, 30 nodes, and you still like each position can take say 10 values or 20 values, you are still in a huge space. So that is, but in general, you could also sample, for example, a topology or the structure without the labels. That you can also do, because you will also get a distribution over the skeletals or the structures from the data. You could also add like that step if that's a concern.
Cool. Thanks a lot.
Any other question? Yeah.
Yeah, thanks. So I have a similar question as you. So you have a fixed graph. So for the first part, you have a fixed graph. So does that imply that then you need to train a separate flow for graphs of different size?
No, because we use these equivariant properties. So we use these TGNs. So these equivariant graph neural networks give us equivariance with respect to size. Invariance with respect to size, equivariance with respect to rotation, reflection, and all that.
And then another question. So what's the role of using a fixed graph for the high validity score? So is that sort of one ingredient? So I assume that you sample the graph from the known graphs of
yes.
atoms.
Yes. So you take a topology, but you could try like other topology as well in principle. I mean, it's you already has, as I was saying, you already have a distribution over the. So it's once you fix your vocabulary, so your vocabulary, whether it's carbon, oxygen, nitrogen, or if you include also the rings, then you clearly get these skeletal structures. And now you get a distribution over these skeletal structures, because you could just take the training data, hide the labels, form these graph or tree representations, and then you get a distribution over these skeletals. So now you can sample, for example, in principle from these skeletals and try to generate. But in principle, if you learn the representation well, but this is an experiment that will not perform. But in case you learned the latent representations well, you could also give new topologies. You could also give new skeletals that you probably have not seen as part of the training. Okay. Yeah.
I have a very basic question. Why graph neural network work on molecules? To me, it's totally understandable if it's work on social network. Yeah. Because usually people with a similar idea connected. But how from the neighbor aggregating we can get information about one atom?
So think, for example, like about this ring. So you have this ring structure. And so if this node is, consider any node in this ring, does not matter. So if you have, for example, 6 layers of graph neural network or 5 or 6 or whatever, then this node is able to aggregate all the information from like outside the rings, 6 or 7 or 8. And so now for example, in some ways, what are the connectivity patterns, what are the local behaviors, And so, for example, you could know that if there is one functional group, if you've seen for sufficient, like there are, for example, parts of the molecules which, are hydrophobic or hydrophilic, or, they have these some kinds of properties. So in principle, if you have sufficient number of layers, then you should be able to learn those representations because they are reflected as part of, for example, the properties or the data that you have. And so underlying densities are there, like for example, and it's all about density estimation. So if you can do density estimation well, then other things kind of automatically always fall in place.
So we are running over time, but I think we still have a question from Kumpula. Can Kumpula hear us?
Yeah, can you hear us?
Yes.
Okay. If I understood correctly, a really interesting presentation. Like you're able to represent these molecules and learn some hidden states that the structure of the molecule with some represented as a graph neural network, and able to learn some hidden states, and then the nodes evolve as some function of some PDE. It's quite fascinating. But my questions pertain to this disentanglement. You showed that the accuracy improved when you add some disentanglement. And I'm wondering, is it because, like classically with VAEs and different Latin variable models, when you impose some constraints on the Latin space and it becomes disentangled, then you need more features to be able to, like, you need more dimensions of your Latin space in order to compete with non-disentangled features. So do you also increase the size of your Latin space as you impose these constraints on to have disentangled features? Or is it like same size?
Yeah, thanks. That's a great question, but not necessarily. For example, like that's why I was also showing these results at the end, where I say, like, for example, for compression. So, there are a couple of things to note here. For example, in case of this property optimization performance, as I say that the incorporating this conditional disentanglement as part of flow empirically improves the performance. But you see, there is also the unconditional part, which does not, sit SIDU. This is the unconditional part, assuming that everything is separable from everything else. So that clearly does not give that much, that much benefit. It clearly is suboptimal with respect to the other models, or many of those models. But incorporating, I think, like this conditional entanglement is the key in some ways, because we don't enforce, separability when it's not there. So this allows the model to be able to learn that. And likewise, in case of the compression, the task that you see on the right side of this of this slide, you see, like, we are having like almost the same size or less size for the representation of the latent space, the representations that we are choosing, and we're still performing better in terms of the accuracy. So you don't really necessarily need to increase the size of the latent space.
What does the number size represent here? Like, it was not clear to me.
Megabyte. It's like, the latent.
Not the size of your data set that you're using, but rather the, like,
this is not size of the data.
It's the size that you compress the molecule to. So like 625 kilobits in the case of like colors -3 or what? Oh, okay, cool. And then second question is on this conditional part. Like, essentially, you're if I understood this last term correctly, you're minimizing the divergence between your like conditionally, like your Latin space, such that they can predict the certain prior conditional variables that you want. Like in the case of the ball, you have the red ball versus the green ball and the blue ball and whatnot, and so you're able to take this picture, do it to the Latin space, and then say, okay, this Latin space, I should be able to predict if it's a red ball or a green ball from the Latin space. So is this imposed with like some further some other parameterization such that you just deconstruct from your Latin space these specific class variables, or like what is this KL divergence of Q with T given Z and A? Like, am I understanding this correctly?
So there is no, I mean, no one tells you which is a radical. So this is an unsupervised notion of disentanglement. So we clearly don't. So that was more for the, like intuition that like why disentanglement makes sense or what does it convey. So we clearly do not have any such supervision. No one is telling that, oh, this is red or, this is the size of this. The idea here is coming to this term. So essentially this T is essentially you can think of it as the coefficients of a basis. In some ways, if I may, give a more intuitive explanation for this, you should think of a latent space which resembles a manifold locally. And now you can think of these TIs as K. You could consider probably K tangent planes. You can associate with any point or the origin of that that manifold. And now what you are able to do is to express, any point on this manifold in terms of these coefficients along the tangent planes that exist. And so here, for example, T is the coefficients along each of these K tangential, K tangent planes that you have. The Z is your latent representation that comes just by, for example, encoding the molecule. So this can be unsupervised as well because you just have a graph convolution network to get that. And so there is no supervision here.
Where does the conditional part come from? Like that it's not clear to me where this conditional aspect is.
So conditional aspect comes in the sense that like after you have this Z, you are not like, for example, saying that this is fully disentangable in the sense that when you use this G hat, so consider like a straightforward VAE, then you just reconstruct whatever is there as part of the latent representation. Here, what we are saying is if you take only the tangential planes, you will still miss out on some information which cannot be decoupled along these planes. So associate and that's where, so you see this discrepancy between Z and Z hat. That's where the conditional aspect comes in. In a simple, when you, for example, are doing writing a straightforward VAE style thing, you would not typically have that. You will just have a Z there, and that's what it reduces to if you go to the unconditional part.